Professor Jarvis has kindly suggested that I should give an introductory talk at this final session of the conference. My period of scientific creativity is past, and I can only give you some personal recollections from the time of the origin and the early development of the theory of stochastic processes. During the 20 years between the two world wars, say from 1920 to 1940, mathematical probability passed through a revolution. For those of us who were at that time young and interested in the subject, it was a time full of stimulating new ideas. There were four men which we regarded as leaders of the revolution: Andrei Kolmogorov and Alexander Kinchin in Moscow, Paul Levy in Paris, and Norbert Wiener at MIT in the United States. The first rigorous treatment of a case of this type took place in 1923 and was due to Norbert Wiener. In some famous papers, he introduced what he called differential space, which in modern terminology is a probability distribution in the space of all real valued functions of a real variable. In 19th century Russia, probability theory had strong traditions with names such as Chebyshev, Markov, and Lyapunov. And in the latter part of the 1920s, it became clear that this tradition was coming to a powerful new life in the Soviet Union. But the real breakthrough came in the year 1933 with the simultaneous publication of the two famous monographs by Kolmogorov and Kinchin. To the present generation of young mathematicians, all this may seem fairly obvious. But in 1933, it was a radical innovation. And it took some time before we were able to see what a vast field of new research possibilities this way of laying the foundations opened.
It's primarily on discrete time, but I should say right now that a rather satisfying theory exists in continuous time, what George Lindgren would call a working theory. But for this and for real applications, in spite of my title, I shall simply have to refer you again to our book.
What I'd like to talk about is the relation between probability and classical potential theory, in particular Martingale theory and classical potential theory. I'd like to show how theorems in one can suggest theorems in another, but more particularly that for certain basic theorems, the theorems are the same, so that they're just different words. For example, in potential theory, they use U and V, and in the probability, use X parentheses with a dot in the middle. But otherwise, these theorems, as we'll see, are exactly the same. The context I'm going to use will be on the left side of the classical potential theory, on the right side Martingale theory. I'll recall that this is the only non-digital blackboard I've ever seen.